When solving problems of motion in two dimension, particularly projectile motion problems, I realize that those problems are just two one-dimensional kinematics problems. And I have equations for kinematics in one dimension. V is equal to V naught plus AT, X is equal to X naught plus V 0 T plus 1 half AT squared, and V squared is equal to V naught squared plus 2A delta X. Those are the equations that I use to solve problems of kinematics in one dimension. When I solve problems in two dimensions, it's handy to sort of rewrite those equations and express them in the context of the two coordinate axes I'm going to use to solve the problem. When I do projectile motion problems, the motion of a projectile is partially x-axis motion. And as it happens, there's only one equation for the x-axis motion of a projectile. And it is that the final x position is equal to the initial x position plus vx times t. You may wonder there when I wrote that, why I didn't write vx naught, the initial x velocity. Well, I've learned that it's a fact of projectile motion, that the horizontal velocity of a projectile does not change. The horizontal velocity of a projectile does not change, and so the initial x velocity, the final x velocity, they're the same. That is the one equation that governs the horizontal motion, just one. When it comes to the y-axis motion, I have three equations. Vy is equal to Vy naught plus the acceleration along the y-axis times t. That's a familiar kinematic equation. I've just added extra notation to make it apply specifically to the y-axis. I might also say that the final y position y is equal to y naught plus Vy naught t plus 1 half Ay t squared. Again, familiar, but written in the context of the y-axis motion of the projectile. And finally, that Vy squared is equal to Vy naught squared plus 2Ay delta y. So it makes my equations look a little bit intimidating at first. I just need to become accustomed to the fact that I'm solving problems that way. So now what I'd like to do is a projectile motion problem that I like to refer to as the Uber problem. In that, it's going to require that I do every possible skill of projectile motion problem solving. If you have calculators available, I'd appreciate it if you'd help me out because we'll have to do some calculations along the way. So I need a scenario that I can solve, and it's going to be a very simple one. I want to imagine here that I have a cliff, and the cliff is some height above lower level here, and I have to choose that number. My drawing skills are a little bit off this morning. See if I can get my act together. So I have, maybe I can't. So I have a cliff here, and I'm just going to make up some numbers for the purpose of solving the problem. I'm going to assume, or I'm going to state, that this cliff is 58 meters above the ground level there. It's quite high, 58 meters. Considering that I'm 2 meters tall, 58 meters is indeed a very high cliff. And a projectile, say a rock or something like that, is going to be launched from up here at the top of the cliff, but it's going to be thrown in such a way that it has an initial velocity v0 that is not horizontal, it is not vertical, but is in fact at an angle relative to the horizontal. So I have to set this initial velocity. I'm going to make the initial velocity be 60 meters per second. That's a very large velocity. It's like fired out of a cannon. 60 meters per second is that initial velocity, and I have to choose this angle. I'll choose the angle that the projectile is launched. I'll choose that angle to be 30 degrees. I'll write that into my diagram. And so this is the information that I have in order to solve this problem. Now you may look at it and say, it seems like the information is quite sparse. Indeed, the information is sparse. I'm going to find a great many things as I go through. Some things that you may notice are unknown. I don't know how long it's going to take the projectile to reach the I guess, canyon floor. I don't know how far it's going to be from the base of the cliff when it gets there. I don't know what its velocity will be when it gets there. I don't know how high it'll rise above the top of the cliff. There are a great many things that I can solve for, and I'm going to solve for them all. As the projectile goes from the top of the cliff to the bottom, it's going to travel along a path that is parabolic in shape. Now, I haven't proven that yet, but shortly I will. The path of the projectile is parabolic in shape. It is not a straight line. I've often seen students make the mistake of imagining that the projectile goes in a straight line from the top of the cliff to the bottom. That, of course, is physically absurd. I can't get answers that way. So I can't do any kind of trigonometry to the path of the projectile. I'm going to have to solve it projectile motion style. Now, The very first example of projectile motion I did for you, the projectile launched horizontally. It didn't have any vertical part to its motion initially. This projectile does. So the very first step that I need to do is realize that my initial velocity, which is 60 meters per second at 30 degrees, is not horizontal velocity. It is not vertical velocity. It is both. It is both horizontal and vertical simultaneously. And so what I need to do here is I need to find out what is the initial x component of velocity, say Vx naught. And I need to find out what is the initial y component of velocity, say Vy naught. I need to figure out what those components are. That is my first task. And that is why I introduced trigonometry into our physics. Because it's trigonometry that makes it possible for me to find the components of a vector. Now, it may be you're not a master of trigonometry, but the skill is quite simple, and it's the same every time. Because what I've realized is that the initial x component of velocity, Vx naught, is equal to V naught times the cosine of the angle. And if you could be ready on the calculators, please, it would be helpful. It's V naught times the cosine of the angle. And since my velocity is 60 meters per second, then I write 60 times the cosine of 30 degrees. Somebody calculate for me, please. What is that equal to? Sometimes our math teachers make us put our calculators into radian mode. So to make sure you're in degree mode when you solve problems. Aaron, do you have this number? 51.96. Let's call it 52. Notice that the horizontal part, the x part of the initial velocity, is less than 60. Well, it have to be, because 60 is the hypotenuse of the triangle in this trigonometric treatment of this. And so 60 is going to be the largest number that I have. So I can now find the initial y velocity, Vy naught, is equal to V naught times the sine of theta, which is going to be 60 multiplied by the sine of 30 degrees is equal to, Yeah, you see, I didn't need a calculator for that because I might take the time to remember that there are some special angles and that the sine of 30 degrees is 1/2. And so I wouldn't need I'm pretty sure your math teachers probably tried to get you to remember that. So I haven't even started to solve the projectile motion problem yet, because my initial velocity was given to me at an angle, and I know that the first thing that I have to do is to break that down into the x part and the y part, because that is how I solve projectile motion problems. Now, back to my problem-solving strategy. I draw a picture, done. I choose coordinates. I draw a picture and I choose coordinates. Well, I always choose the same way when I'm solving projectile motion problems. There are two aspects to it. I always choose the launch point, the initial point, to be 0 in both x and y. I always choose the initial position to be where the thing is launched from. Now, you may look at this problem and realizing that the projectile will ultimately land in the canyon, you might look at it and say, well, you know, I'd rather choose 0 to be down on the ground. You can do that. You get the right answer anyway, because the choice of coordinate system when you're solving physics problems is arbitrary. So I choose that as 0, and I always choose up and out to be the positive directions. I'll signify by drawing that little icon in there. Up and out are the positive directions. I don't really care about out so much, but up. I always choose upward to be the positive direction, because if I always choose upward to be the positive direction, then when I write my list, the acceleration will always be negative 9.8 meters per second squared. So I chose my coordinates. Now it's time to make my list. But I must write one list for each of the coordinate directions. So I have to write two lists because I'm solving two one-dimensional problems simultaneously. So first I'll write the x list. Initial position, final position, initial x velocity, final x velocity, time, and acceleration along the x-axis. And I've added notation. I've added notation to make sure that every quantity I realize that this is the x component of it. I don't have to add extra notation to t because the time is the same on both lists. But everything else needs a little bit of extra notation. I'll need a second list. I'll need a list for the initial y position, the final y position, the initial y velocity, the final y velocity, the time, and the acceleration along the y-axis. Again, adding a little bit of notation to each axis in order to make it clear what it is that which axis it is that I'm looking at. So now that I've written the lists out, I need to go down each list and fill out what I know and what I don't know. I want to make sure that the units and the signs are correct, but I also want to make sure that I don't just jam in some numbers because I, am hoping for the best in the problem. I have to think carefully. If I don't know a quantity, I have to be honest about it and put a question mark. And so I begin thinking only about the horizontal motion of the projectile and not the vertical motion. Only the horizontal motion. So numbers like 58 meters, which is the height of the cliff, irrelevant. Numbers like 30 meters per second, which is the vertical component of the initial velocity, irrelevant. I'm only thinking about that which is horizontal. I'm only thinking about that which is x-axis. Initial x position, I chose it. It's 0 meters. Final x position, that is where it ends up from the bottom of the cliff, I have no idea. That's one of the quantities I'm going to find. I do not know where it ends up in the end. Initial x velocity, you see, I conveniently, by being careful in my problem solving, I already found it. It's 52 meters per second. Now, every once in a while, it happens that I reveal to you where honors physics students commonly make their mistakes, and this is it. I've seen students do all kinds of wrongness here. One is to take the full 60 and put that number there, where I've just written 52. Take the full 60 and put it there, and then when they get over here, go, oh, gee, I don't know, I already used the 60. I'll just make that 0. That's not correct. That's not appropriate. I've seen students put 60 in both places. What the heck? That is not thoughtful. That is not physics. And so that should be, strongly penalized. Now, what belongs here is only the x part of the velocity. Only the x part of the velocity belongs here. Vx, the final x velocity, well, in principle, I don't know it. Until I remember that when I investigated projectile motion, I was able to reason out that since the force of gravity is vertical, the influence of gravity is vertical, that there is no horizontal acceleration. There is no x-axis acceleration. In fact, I'll always write that to be 0 meters per second squared. Since there is no x-axis acceleration, the x velocity will not change. And in your problem solving, in this honors physics class, those two numbers, Vx naught and Vx, will always be the same. That's great for you solving problems. They're always the same. Things that you can rely on. How much time does it take for the projectile to reach the bottom of the cliff? I have no idea. I have no idea. Now I've done the X list. I have all the things with the correct units. I know what my unknowns are. Now I'll do the Y list. Initial Y position is 0 meters because I chose it to be that. So no trouble there. Now, here's where a little bit of care needs to be taken. The final Y position is at the bottom of the cliff. That's where it's going to end up. With upward chosen as the positive direction. So this must be negative 58. You might look at that and say, if you had chosen down to be positive, then it would be positive 58. Isn't that better? Well, then you have to think about what your acceleration is. I don't play that game. I choose upward to be positive, always. I make my choices consistently so that it simplifies my thinking about the problem. The final position is down from 0. So it's negative 58. I'm totally cool with that. Initial Y position, initial Y velocity, good for me. I already calculated it. Vy naught is 30 meters per second, not 60. 60 is the whole velocity. On this part of the list, I just want the vertical part of the velocity. I don't want the whole velocity. So I wouldn't dare put 60 there. Final Y velocity, ooh, I know 0. What? Why are you saying 0? Well, because it hits the ground and goes flat. And then its velocity is 0. It's sitting there on the ground. Look at it. That's not what we mean by the final Y component of velocity. We mean just when it arrives. If you think that it doesn't have a vertical velocity when it arrives, go stand there. Let it hit you. It has a final vertical velocity when it arrives. In this case, it's going to be very large. And I don't know what it is. So I have to put a question mark here. It's a common mistake to force that to be 0 just because, and then the problem can't be solved, right? You'll get all kinds of nonsense out of your equations. That's never going to work. So it's really important to realize that I don't know that quantity. Time, I didn't know it on the x-axis. I don't know it on the y-axis. Acceleration, I don't even have to think about it. The acceleration is caused by the influence of gravity, which creates an acceleration of 9.8 meters per second squared. I've written it negative because I chose upward to be positive. Done. I don't even have to think about it. That's what it is. And so I've come to the end of my list making, which is where all of the physics happen. Someone's trying to solve a problem, can't get the answers. I'm going to look at their lists and I'll know. whether they have a problem with their understanding of the physics of the situation or whether they have a problem with doing math. Now, I'm going to do a little bit of math. I mentioned previously with one-dimensional kinematics problems that there's more than one way through a problem. There's more than one way through a problem, and so the same is true in this situation. More than one way to get through the problem. So what I'm going to do is do it a little differently than I've done it in the past. My habit right now would be to find the time first. And I can, and I'll show you why. If I take the fourth equation that I've written here on my list, y is equal to y naught plus vy naught t plus 1/2 ayt squared. I know everything, comparing it to my y list, I know everything on this list except time, which means, algebraically, I'm assured that I can find the time. However, it is quadratic. It is quadratic because the time appears, and then again the time appears squared in the equation. It is a quadratic. So I'll have to use the quadratic formula. Very often students get upset about that and they say, oh, I don't want to use the quadratic formula. Well, I can sort of get around it, but we'll see in a moment what the consequences of that are. Instead of trying to find the time first, I'm going to go for the initial y velocity first. Now you might say, Scheidly, I would prefer to start on the x-axis if you don't mind. Sure, let's start on the x-axis. I do not know the final position, and I do not know the time, and there is only one equation for solving for the x-axis motion. I do not know x and I do not know t. I can't do anything on the x-axis, which is why most, not all, most projectile motion problems start on the y-axis. So I'm going to try to find vy, pardon me. I'm going to find vy, and I don't know time. Remember, I'm solving one-dimensional motion problems here. When I do not know the time, I know exactly which equation to pick. I pick the equation that doesn't have time in it. I choose the equation vy squared is equal to vy naught squared plus 2a delta y. And I write my equation there in standard form. I should say ay delta y. I write my equation there in standard form, and now I'll get busy doing the math. I do not know the final y velocity, vy squared, but I do know the initial y velocity is 30, then squared. I know that the acceleration is negative, so I'm going to write in a negative sign there. 2 times 9.8. Do you see how what I've done is I've taken the negative sign of the 9.8 and I've simply put it out in front of the whole works, simply because I believe that it looks better that way. Delta y is the change in the y position. That's final y position minus initial y position. So I'll write it out here. Final y position minus initial y position. That's negative, looking at my list to cheat a little bit, negative 58 minus 0. Now we see where we start to get in trouble solving these problems. There's lots of negative signs whizzing around all over the place. So I have to be careful. The negative 58 that appears here is going to make this term overall positive. So if you wouldn't mind, please, on your calculator, I can already see some buttons going. Calculate for me 30 squared plus 2 times 9.8 times 58. I wouldn't put in all those negative signs because I'll use my head to do math. I'm using my calculator to do arithmetic. So if I calculate 30 squared plus 2 times 9.8 times 58, I get what? 2036.8. So I'm going to call that 2037 meters squared per second squared because I didn't take the square root yet. Would you please take the square root of that, please? I'm sorry? Yeah, sure. I'm going to call that 45. I don't have to worry about significant figures, do I? Because this is fictional, this problem. Look, I got the answer. Yeah, but I didn't get the right answer. What's wrong with this answer? 45 meters per second. Declan? Yeah. The thing about using this equation to solve projectile motion problems, or freefall problems for that matter, is that the equation involves taking a square root at the last minute. Your calculator is always going to cough up a positive number. But this projectile, when it arrives at the bottom, is going downward. The projectile, when it gets to the bottom, is going downward. That's the direction I've chosen to be negative. So as the physicist in this situation, I have to add that negative sign because my calculator doesn't know that I'm doing physics. Scheidly, you and your negative signs, it doesn't matter. Yes, it does matter whether that final velocity is positive or negative. Because now that I have that final y velocity, I'm going to want to find the time. Now that I have the final y velocity, I'm going to want to find the time that it takes. So I'll give myself a little separator here to clear what I'm doing. The easiest way to find the time in the y-axis motion is to use Vy is equal to V naught y plus Ay times t. So that's what I'm going to do. Vy is equal to Vy naught plus Ay times t. Now, I prefer, when I'm solving one-dimensional motion problems, and indeed, again, two-dimensional motion problems, I prefer to do the algebra first and then to sub the numbers in. So I'm going to solve this for the time. When I solve it for the time, it's the final y velocity minus the initial y velocity divided by the acceleration along the y-axis. The final y velocity I just found is negative 45 minus the initial y velocity, which I can read off my list, is 30, divided by the acceleration, which is negative 9.8 meters per second squared. Now look, if that's not negative 45 when I plug it in here, I'm surely not going to get the correct time. I cannot get the correct time if I do not plug that in as negative 45. So you calculate as negative 45 minus 30 divided by 9.8. The negative signs will go away, and I get a positive value for the time. What is that positive value for the time? 7.7 seconds. This is a very high cliff. So 7.7 seconds sounds to me like a decent time. That seems to me like a time that I would expect. So now on the y-axis of my motion, I know the final y velocity and I know the time. I've calculated both of those. My y list is complete. My y list is complete. My x list is not. The time that I calculated, 7.7 seconds, makes its way over to the x list. So all I need to do now is to use the one equation that I have for the horizontal motion, and find the final position along the x-axis. So x is equal to x naught plus vx times t. Well, the initial x position I know is equal to 0 because I chose it to be 0. So that simplifies this equation even further. X is going to be equal to the x component of the velocity, which I have not yet used in my solution. It doesn't matter whether it's initial or final, because on the x-axis, the velocity does not change. So that x velocity is equal to the x velocity, which I found is 52 meters per second, multiplied by my time, which is 7.7 seconds, and I get what for the final x position? 400.4. So I'm just going to call that 400 meters, nice and round. I have now found everything unknown on the list. Everything unknown on the list. But I haven't really found everything knowable. I found everything unknown on the list, but I haven't found everything knowable. Because I haven't found the final velocity of the projectile when it reaches the bottom of the cliff. No, Scheidly, you did. We calculated here, it's negative 45. No, that is the final y component of the velocity. That is but a component of the velocity. Oh, sorry. What I meant to say was 52 meters per second. No. That is the x component of the velocity. I have not yet found the final velocity. The final velocity is going to be found by putting it back together again. I'm solving the problem by taking a two-dimensional thing, cracking it down into two one-dimensional problems, and now when I get to the end, I got to put it back together again. Well, in the context of right triangles, putting it back together again means vx squared plus vy squared square root. That is how I reassemble the components of the final velocity. So when I do that, it's going to be the square root of, these are squared vx and vy, so I'm not really concerned with what their signs are. It's going to be 52 squared plus 45 squared square root. Quick. 69 meters per second. Oh yeah, you found the final velocity. No, I didn't. I found the magnitude of the final velocity. Velocity is a vector. It has a magnitude and it also has a direction. And I haven't said anything about the direction, so I must calculate. Again, I turn to trigonometry and the fact that the angle of this final velocity vector can be found by computing the inverse tangent of the y component divided by the x component, because that's the opposite component divided by the adjacent component, and that is how tangent works. When I do physics, I will never enter negative numbers into this inverse tangent calculation. Never going to put a negative number in there. What I'm going to do is I'm going to take the inverse tangent of the y component of the velocity, written as positive, which is 45, and the x component of the velocity, which is positive anyway, which is 52. And what am I going to get as my answer? 40.8. So let's say 41 degrees. Well, what does it mean? What it means is that when the projectile arrives at the ground, now here I'm imagining the impact point here. When the projectile arrives at the ground, its final velocity vector v will look something like this. So here's the projectile, sort of, I guess it's sort of spherical projectile, like a cannonball here. Its final velocity v will look like this, and the angle that we've just found is the angle down from the horizontal. So now that I know the magnitude and the direction of the final velocity, I know the final velocity vector. But I have not yet found everything. I found everything on the list, but then I realized I didn't know the final velocity. So I found the magnitude and the direction of the final velocity vector. Now an extra thing that I would like to know is what is the maximum height to which the projectile ascends? That point at the top of its arc is another piece of information that I might learn about this particular motion. And so my list is not really going to help me do that, because my list describes the motion from the initial position at the top of the cliff to the final position at the bottom of the cliff. Now, what I could do, and it would be very laborious for little benefit, is I could make a new set of lists now, where all of the initial quantities were the same, but I would change the focus of my list so that the final values would be at the maximum height. I'm not going to do that, because the revelation that I would have then is quite simple. At the maximum height of the projectile, the x-axis velocity is the same as it ever was. Because during projectile motion, the x-axis velocity does not change. However, the vertical velocity is 0. At that instant, when the projectile reaches its maximum velocity, the y component of the velocity, vy, is equal to 0 at that point. And so I'll be able to solve for the height above the launch point simply by applying vy squared is equal to vy naught squared plus 2ay delta y. And that'll get me the result that I'm looking for. The final y velocity, I'll force that to be equal to 0. The initial y velocity is still the component that I had found at the beginning of the problem, because I'm still launching from the top of the cliff. So that initial y velocity is the same. The acceleration is still negative 9.8 meters per second squared. So what I'm doing is solving for delta y. And when I do, I'll find that delta y is equal to negative vy naught squared divided by twice the acceleration along the y-axis. Now, you might have a little concern that that's going to work out to be negative. Of course it's not, because the acceleration is negative 9.8 meters per second squared. And so, plugging in the numbers here, I have negative v naught y squared. Now, v naught y was 30, which I'm going to square, divided by 2 times negative 9.8. And if I could get a little help here on the calculation, don't bother to put the negative signs into your calculator. They're going to cancel anyway. So if you would please, 30 squared divided by 2, and again divided by 9.8, and you get what for delta y? 45.1, I'll say 45. And so what I discovered, I'm sorry? 46. I thought you said 45.1. Oh, 0.9. So 46 meters. So the final, or the height above the launch point that it rises is 46 meters. Have I found everything about this problem? Well, not really. There's another thing that I could ask, and that is, what is the total vertical distance traveled? How far it went up, how far it went down, calculate all of that stuff. But I think I'm satisfied that I found a lot of useful information out of what began with very limited initial information. This is the Uber projectile motion problem. It contains every skill that I need to solve every problem of projectile motion that I'm likely to encounter.